Welcome everybody to the fifth lecture of our machine learning class. Today we're going to talk about principal component analysis. So let's start by looking at something that you've seen a couple of times already, distribution of data points in two dimensions, x1 and x2. And what you should see already that the data is correlated. Yeah? So if we increase x1, we see an increase in x2 as well. And and that's not something that's rare or impossible. That's pretty common. So think of data like that. So I don't know, we have patients and we measure different things for them. So the length of the index finger and their body length or the body height. Yeah? And obviously these two variables are connected. Yeah? So there's like a hidden genetic component, let's say, that determines how much we grow. And still we have some spread, right? So measuring a large finger could still lead to measuring a small person, but basically this is the underlying, let's say, rule. Yeah? The larger the finger, the larger the person, or vice versa. So the data is really living in one dimension. Yeah, we can describe this as a line, like we saw 2 lectures ago, and a given data point that has two dimensions, x1 and x2, can be described with a little bit of an error as just one number, yeah, which is maybe a number that tells us how far along this line we have to walk until we meet, let's say, a point in this two-dimensional space that is closest to our point. Yeah? And so a small person with a short finger then obviously has a smaller number, yeah? Alpha here. And sometimes the remaining spread is also something that we still want to look at. So PCA will provide us with something that's called orthogonal basis. So that's really just a set of vectors. And those vectors are orthogonal, yeah? Like the ones that we start with, x1 and x2 are directions in our space. And so we could have also different vectors, and we call them principal components. So the principal components of this data distribution are orthogonal vectors, and the first principal component is the direction of maximum variance, or the direction in which the data has the greatest spread. And obviously this works in many more dimensions as well. So let's think of a data distribution in this ellipsoid kind of shape. Then the first dimension would be the dimension that has maximum spread or maximum variance. And if we reduce the data to this one slice of bread, let's say, then we still have two dimensions left in which we could then try to maximize variance. Yeah. So the second principal component obviously then would be this dimension, and then the remaining. Remember, they all have to be perpendicular to each other. The third one then is the result of the first two ones, but so this works in higher dimensions as well, and especially in higher dimensions. That's something that we use PCA for as well. So PCA, what do we do with it, and why are we doing this? Well, like you saw in the previous slides, when your data is correlated, so x1 gives you information about x2, that's something that sometimes we don't know, and we don't want. And so we want to decorrelate the data. So we want to transform our original data point into another data point that also has two factors. But now knowing one coordinate doesn't give us information about the other. And sometimes we want to throw away a couple of dimensions because they're sufficient to describe the data. And this improves our machine learning classifiers, for example, having to cope with a lot less numbers. And this can be done to compress the data, but also to extract those features of the data that are relevant. And relevance really here translates into the data set shows a lot of variation into these directions. PCA can also be used to standardize and normalize the data, a process that's called whitening. So the distribution that we just saw, it looks like an ellipse, and projecting this down to like a spheroid circular distribution is what's behind this. We're not going to look into this, but maybe Max in the assignments can talk about this. And the second thing, or the last thing here, is visualization purposes. So PCA is often used to visualize high-dimensional data. And one example is this plot here that I've found on Wikipedia. These are 2 dimensions in a 784-dimensional space. And the samples in this high-dimensional space are actually images. So there is another way of visualizing these, because they are just pixel brightnesses. Each of these 784 dimensions is 1 pixel, and if you reshape them into a 28 by 28 pixel image, then of course we can just look at this as an image. And MNIST is a data. MNIST is this handwritten digit data set that we've seen before, and Fashion MNIST is now showing us different types of clothing, so shoes and t-shirts and whatnot. And so this data set was created by the colleagues from Zalando. So obviously they had a couple of these samples, and the community was happy about this data set. So now back to the visualization purpose. We sometimes have data points that are not images, but just I don't know, many measurements of patients, for example. And then by visualizing these high-dimensional data, how different variables correlate, how the data spreads along different dimensions, helps us understand the data set, helps us understand, create hypotheses, how to classify, how to process the data, and so on. So when we say, okay, we seek a vector W that maximizes the spread of the data along this direction, what do we actually mean by this? So let's have a look at variance first. Variance in 1 dimensions is a property of a data distribution. So for example, look at the height of, let's say, female humans, and then the data points that may look like this. So a distribution that I don't know, varies between small people and huge people, and then obviously most of those values are here, let's say at 170 centimeters. And then if we look at the density, this is a nicely well-shaped curve, which gives us the probability of a sample being, having a certain value. And this model of a normal distribution has 2 parameters. We can look at, okay, where is the center of this distribution, and we calculate an estimate of this underlying distribution by just averaging all the data samples. So all of these green points here are summed up, and then we divide by the number of samples that we have. And the second number, that's the variance that we want to look at. That's really the average deviation of each data point to the mean, to the center of the distribution. So we subtract each of these data points from the mean, we square it, and then we average these squares. So you've probably seen sometimes the sigma without the square. That's called standard deviation. And so, for example, if we have the mean and count how many data points fall into mean minus 1 standard deviation and mean plus 1 standard deviation, that's something like 60 to 70%. And then if we have 2 standard deviations, this goes up to 94 or 95% or something. Yeah, so this is a way to describe how wide this curve is. Now, let's look at how this one-dimensional description of variance can be applied to an n-dimensional data space. And so the first thing that we want to do is we center our data, because that makes things way more easy. Yeah, so what we do is we take our data points, the original data points, we calculate our x bar, and then we take every single data point and subtract the mean from it. And so in the next run, what we can do then is to calculate the mean again, and this should be 0. Yeah, 0 could also be here a vector of zeros, right? So each of these components, each of these dimensions would be 0 on average. That's how our data distribution is set. So now let's assume we have our vector W, and that's supposed to be the direction of the data with the maximum variance. How do we get this variance? We know what the one-dimensional variance is, but how do we obtain it in a two-dimensional space? Now, we need this vector, and let this vector be this blue one. And let's say it's restricted to length 1. So what's really important is really the direction. Yeah? Now, what we now do is we project a given x onto this direction. And that's basically done by using the dot product. So W transpose X gives us a scalar value, a one-dimensional value, that corresponds to the orthogonal projection down on this W. And since 0 was already the mean, this number gives us the deviation from the mean. And you see where I'm going. If we do this for all the data points, we can collect all these deviations. Yeah, and what we see is that most data points will probably fall into deviation 0, and the further we go away from 0 in this or in the other direction, the number of data points get fewer and fewer. So what we really want to do is we want to find this W, and that's not probably the one that you see here. That's not the one that we are looking for, because it's not really the direction in which the data has maximum variance. So what we really want to do is to find a W that maximizes this objective. So W transpose X I is the deviation from the mean of the data point xi. So that one-dimensional red value here. And then we square it, and then we sum it up. Yeah, we could divide it by the number of data points, but anyway, it will be maximum if we don't divide it and so we just keep it simple. Yeah? So this is our maximization criterion. And before I show you how we would usually do it, I will show you Oja's algorithm. That's a Finnish researcher, and it's an iterative scheme that gives us, in the end, the direction that maximizes the variance. So basically, these are 4 steps that you do in a loop until you think you're done with it. So you first pick a random x. I've done that for us already. And then we update our w that we randomly choose to, as an initial condition. Could be any of these x's or any vector pointing anywhere in this world here. And then we update it using this equation. I'll explain this in a second. And once we're done with the update, we normalize and we decrease one of these parameters here, gamma. And what this means follows in a second. Now let's have a look at first at these dot products here. So W transpose X was, as we just discussed, this scalar value that gives us the orthogonal projection onto W. We have that in the update equation. We have it twice. So let's have a look at this one first. So what happens if the data point is in the opposite direction of W? Well, the projection is still a scalar value, but it's negative. Yeah? So what about a data point that is orthogonal, so perpendicular to W? Well, the dot product will be 0. Yeah. So given that, let's say this is a negative dot product, this will scale our vector W here, right? So dot product with X times W flips our original W into the opposite direction. And since it has length 1, it's exactly as long as the projection was. Yeah? Now, then let's have a look at X minus this vector. So X is this. X minus this vector points to X. Yeah? So this way. And then the second dot product that we highlighted before comes into play because this was negative, remember? So this flips this vector, and then we add it onto W with a scalar. We call it learning rate, gamma. But this flips it into this direction, and the new vector W here will be then updated in the next iteration. Yeah, and so going over the data over and over again will hopefully result in the vector representing the first principal component. And each of these data points really drags the W into the correct direction. Those data points that are in the positive half space, so W transpose X is positive, will attract W, and those in the negative half space will repel it. So in the end, this leads to a good representation of this principal axis. Now, so let's assume we have converged here. Yeah? So decreasing the learning rate will eventually make our updates smaller and smaller and smaller, and at some point the vector W will not move again. Yeah. And in your assignments, you will have to check which is a good strategy. So where do we start with gamma, and what are the steps that we can decrease it? So yeah, find this empirically. Now, well, that's a good strategy for finding the first principal component. Yeah? So the direction in which the data is maximum. And in 2D, it's easy because then the remaining direction is in this direction, right? Because we know it needs to be perpendicular. Now in higher dimensions, that isn't the case, and what we need to do is we need to subtract the data's spread into W's direction. And we do this by, well, just doing what I just said. So we take every x and we look at the projection of this x onto W, which is a number, and then we scale this vector with this scalar value, and then we subtract this vector from x. So it looks like this. Let's take this x again. It has this projection, this red value, and the scaled. So it's a flipped version, right? Because it was a negative dot product. This W is, you can't see it well, but it's violet here under the red line. And now x minus this vector W, this flipped and shortened vector W, is this vector. Yeah? And so we've transformed this point to a point that lies here, and if we do this for every point, we squeeze everything together onto this one-dimensional subspace in the two-dimensional space. And then we can do this again, this procedure, and then find the new direction. So that's usually not the way we solve the PCA problem. But Oya's algorithm is, I think, a nice way to visualize what's going on, how the data is distributed, and what those vector operations actually do, now we're gonna show you how we usually solve PCA, right? So how do we get those those vectors W that correspond to those directions with the greatest variance? And let's start again by looking at this term here. So W transpose Xi was Xi projected down on W. And that gives us the scalar deviation from 0. Squaring it and summing all these things up is the one-dimensional variance along W. Yeah? And so let's take this and we can rewrite this as just twice. So twice this term. So multiply W transpose Xi times itself. And since we can turn W and Xi around, the dot product will be the same. Let's rewrite it like that. And now W doesn't really depend on I. We can pull this out of first their individual parentheses and then out of the summation. And we'll end up with this expression here, which is interesting because here in the middle we have this matrix X transpose X. So what is this? Well, let's just take one sample for a moment, one data vector Xi. So what we have in this matrix is how the products of the first coordinate with itself, or the product of the first coordinate with the second coordinate, or the second with the second. And so again, these are deviations from the mean, right? So these are so-called covariances, and that's why also this matrix is called covariance matrix. Disregard the factor, right? So the covariance matrix would be X transpose X divided by N. But we can rewrite the maximization criterion here. So the stuff that we want to maximize as W transpose sigma W. Sigma is the covariance matrix, one of our favorite matrices, famous matrix, and you should know about this matrix. Covariance is actually a generalization of variance. You'll see this sometimes written as cov of two random variables, x and y, for example. And if you look up the definition, you'll see something like that. So you have samples drawn from these random variables, and these samples are compared to their mean, to their individual means, x bar and y bar. So you look at the deviations, how much they vary from their individual means, and then you multiply them. So you look at how they co-vary, right? How they both vary together. So then in a one-dimensional case with only one variable, one random variable, you often see also this kind of notation. So covariance of x with x, and then this is the variance. This is just a simple one-dimensional variance. Yeah. So x transpose x is, as I said, the covariance matrix, but n times. And for any mean-free dataset X, the covariance matrix looks like that. So you have, it's a symmetric n by n matrix. So n is the number of dimensions. So in a two-dimensional case, 2 by 2. And then you have the diagonal filled with the variances. So each dimension that you have, so in 2 dimensions, it's this x1 and x2, each has their own variance. And then you have up or left and right of the diagonal, you see those mixed covariances. So how much does the first dimension vary with the nth dimension, for example? Yeah. So let's do this for a two-dimensional example. This is a data cloud that was generated by Louis. It's really flat, so it has a lot of variance along the x1 dimension and almost no variance along x2. And that's exactly what we see in the covariance matrix. So sigma 1 squared is huge. Sigma 2 squared is small, and also the covariances are small. And if we look at the opposite, so a large spread along the second dimension, that's exactly the reflected by the covariance matrix as well. And now if we have a distribution like this, we also have large covariance, right? So remember, this is sigma 1 times sigma 2. So if there's a deviation from 0 into one direction, in the positive direction, and you also have a positive deviation from 0, then you have a positive value. And it's symmetric because sigma 1 times sigma 2 is sigma 2 times sigma 1. Yeah. Now I forgot to tell you what's so cool about the covariance matrix. So look at this term. That's the variance. Yeah. So that is an expression that that we derived 2 slides earlier, that gives us the variance of all data points along this direction W. Now, remember we had 2.4 million data points, and they're all two-dimensional, and then we put them all into this matrix. And the cool thing is that we don't need any of these individual data points anymore for this projection. Yeah. So the covariance matrix sigma contains all this data, contains the variance, and we don't have to compute the variance for each of these, for each of these possible W's that we may want to come up with. We don't have to iterate over all data points again. We just take the sigma. Yeah, so that's cool. But now, so this slide here reminded us of the fact that we wanted to maximize this. And this doesn't work. Why? Why do you think this can't easily be maximized? I'll leave you a little bit to your thoughts. So, well, I mean, this could be made huge, yeah, because we can choose W to be really huge, but that doesn't give us a solution that we want. Yeah. So, to limit the length of W, we use something that's called a Lagrange multiplier, which is just a part of this optimization criterion that corresponds to what we want. Well, we want to keep W to length 1, so we say W transpose W, which is the square of the length, but will be 1 if the vector has length 1. 1 minus this needs to be 0, right? So we want this penalty to not hurt our actual optimization criterion. Now, if W is way longer, then this will be negative, and it will hurt this. And if it's too small, well, then obviously this criterion isn't maximum as well. So this ensures that we can actually solve this and find a solution. And how to find the solution? Well, we take this criterion and set the derivative of it with respect to W to 0. And so let's have a look. Maybe we can simplify things. So first we have W transpose sigma W plus lambda times this. So let's pull lambda in here. So plus lambda minus lambda W transpose W is what we simplify this to. And then the nabla operator is that's the derivative, the partial derivative, the gradient of this with respect to W, can be distributed into each of these terms here. Lambda is not depending on W at all, so will be cancelled. And then we have nabla W transpose sigma W minus nabla lambda W transpose W, and then what we end up with is so basically those W's fall away, and then there's a 2 also that can be cancelled. So in the end, we have something that looks like this. So sigma W equals to lambda W. Yeah, and so this means W is an eigenvector of this matrix, sigma of the covariance matrix, to the eigenvalue lambda. And so if we multiply W transpose to each of these sides, and W transpose W is 1, remember, then we see that the variance, so that's what we wanted to maximize, the variance is lambda. Yeah, so if we have this vector W, which is, by the way, the eigenvector of sigma, the eigenvalue gives us the variance of the data along this direction. So in practice, it's as simple as this. We take the data, we remove the mean, we calculate the covariance of the data, and then we use some linear algebra package to extract eigenvectors and eigenvalues. So if you use Python, there's a function that's called eig, and it takes the covariance matrix and provides the eigenvalues and the eigenvectors in these two matrices. And the covariance obviously can be produced as x transpose x, but also, I mean, you can find a function that helps you with that as well. But really, this is 3 lines of code. Now, remember we wanted to decorrelate the data. So we have in our data, which is already mean-free here, a linear relationship, a correlation, negative correlation of x1 and x2. And what we want to do is we want to take the data set, each of these points individually, and create a new data point from each of these, and therefore a new data distribution that shows no correlation. And we do this by using our data matrix X and our matrix of principal components W, and multiply these two together. And what we get is visualized here in this plot. So let's say the first data point in X is this yellow data point here. And the first principal component in W is this vector. Yeah? They are all sorted. So those vectors with high variance in the beginning, and then they're decreasing in variance. So this vector times this vector, remember, it's just a projection of the data onto W, which is this red scalar value, and this is the 1 point here. Now, if we then use the orthogonal second principal component and this data point, this times this gives us a negative value here, and that's the second coordinate of our transformed data y. Yeah, and so by multiplying all these W vectors here to the same X gives us a number of coordinates which are in the coordinate frame of our principal components, and therefore if we plot them in our Cartesian coordinate system here again, so x1 is the first component, x2 is the projection on the second component, it will look like this. So this is a decorrelation of the previous decorrelated example. Now we can do this multiplication with the full set of principal components, but we also could reduce the number of principal components, so the resulting dimensionality of y of our new data is reduced. Yeah? So for example, we just take one of these components and we can reduce a two-dimensional coordinate to only one dimension. Yeah? So these vectors are really only scalar values, or if you had a 1 million dimensional space, you can reduce it to 10 dimensions and so on. Yeah? Now, reducing the dimensions of your data usually results in a lossy compression, right? So look at this distribution here. Obviously, we lose information. Now, we can reconstruct from those lower dimensional coordinates samples that are in the original data space by just projecting them onto those principal components. Yeah, so x times w is our y here, yeah, and then multiplying the w transpose again onto y gives us a reconstruction of our samples x. So for example, think of y being the one-dimensional data points, and then we multiply them by the each, by this one principal component that we found, right? And by this we scale this one vector, this first vector here, and so we obtain this reconstruction. And we can quantify how good this reconstruction is by comparing the original data point with the reconstruction, for example, by applying a 2 norm, and then we have a distance for each data point, and also a distance for the whole data set that we can then use in different applications. And one of those applications is something that was published quite some time ago. So Turk and Pentland published this paper in 1991. And here the task was to detect faces, right? So we have small like cut out images, and they may show faces like the ones here or not, and our task is to detect them. Yeah? So provide 1 when it's a face and provide a 0 when it's not. And the idea here is to use PCA to extract the principal components from a data set like this. So imagine we have tens of thousands of these kinds of faces here, and then from this data distribution we look at which are those components with maximum spread. Yeah? And this is what the result looks like. So eigenfaces is what they call those eigenvectors. Yeah? And since they are images, you can display also these vectors in, as an image. And you see the first components are corresponding to the brightness, the overall brightness of the face, right? So these could be multiplied by negative values too, and so they get brighter or get darker, or shades, gradients in x, y, or x directions and y directions, and then other features like nose, eye regions, and the mouth. And so by combining those vectors linearly with certain amounts of weight for each of these components, we can reconstruct faces. And the point of this paper was we can also build a classifier from this very simple classifier that just looks at the reconstruction loss or the reconstruction error, and then compares it to a threshold. So if we had an image that we project into our principal component space and then reconstruct the image and compare how far or how close this is to the original, we can compare this then to a parameter, theta, a threshold. And if the loss is smaller than this threshold, then we say that's a phase. And if the loss or the error is larger than this threshold, then we say it's not a phase. It's a very simple algorithm, and I think that's a very nice idea how to use PCA. And so we've reached the end of our lecture. I hope you enjoyed PCA. Your tasks will now be to implement the iterative scheme described by Oya, and of course the quick solution, quick and exact solution with eigenvectors and eigenvalues. I hope you have collected a couple of questions for next Monday. Enjoy the rest of the week. See you all on Monday.